Okay, so my name is Pedro Szekely. This is Mayank. We're from the Information Sciences Institute in the University of Southern California. And so this is basically based on work that we've been doing over the last 3 years. And the basic idea here is the idea of the unusual domains. So we've been working in many unusual domains, and so we will be going over that. So here's the plan for the day. So we will first talk about what do we mean by unusual domains. Then we'll discuss knowledge graphs, how we build knowledge graphs, and then have a sort of extended demo of a case study of building a knowledge graph. Yeah, the case study is actually quite interesting because it was done by two folks from the SEC who worked on this for about 5-6 hours. And I'll show you what they did with the tools that we provided them. And then after the break, we'll go into basically data mining ideas and more of the sort of research ideas. So knowledge graph completion, entity resolution, probabilistic soft logic, embeddings, and then how do you search the knowledge graphs. Okay, so let's get really started. So what's an unusual domain? So I'll give you examples. So one of the examples we have is disaster assistance in regions using low resource languages. So low resource languages are languages for which there are very few linguistic resources on the internet, and basically there's no Google Translate for them. And the idea is to basically mine social media data and news to give the responders some idea of what's actually going on in a disaster area. And I list there some of the languages that are being used in this challenge. They are all languages that many people haven't heard of. And so you want to do very simple things like identify areas where people are in greatest need. And what is the need? Do they need water? Do they need food or shelter? Also try to identify threats to the relief personnel. If there are disturbances or riots, you want to alert the rescue personnel to avoid those areas. And the challenge, the technical challenge, even after translation, is that you're going to get this of super noisy data, because you can imagine a translation system trained from nothing is going to give fairly noisy data. Other domain that we've worked on is identifying illegal firearm sales. So in the US, it's legal to buy and sell firearms within the law. And most sales are legal, but some are illegal. There are people who are not supposed to be able to get guns. There are people who are not supposed to both buy and sell guns or sell guns across state lines and so on. And so the idea is, can we mine this massive set of online advertisements and forums to actually find the people who are doing this illegally? For example, find people who are buying guns on behalf of somebody else who is not allowed to buy guns. Find stolen guns on the classified ads. So these are all domains where there is a lot of public data and very interesting questions. Identify counterfeit electronic vendors. So it turns out a lot of the military equipment of the U.S., the aircraft carriers, ships, airplanes use fairly old chips that are no longer being manufactured in the US. And so they have to import them from online vendors, mostly in China. And they have figured out that a lot of the chips that are being sold as new are not new, and some are actually have a Trojan horse in them. And so the idea is how to detect the vendors of fake chips, also from the sort of classified ads and from shipping, labels and so on. Of course, the challenge here is that many pages are in Chinese. There are many fake images in the catalogs. And this idea of deception is something that's going to sort of be recurring in many of the sort of unusual domains. This one is pretty obvious. The dark web has a lot of narcotics vendors. There's all the marketplaces on the dark web and forums. And one of the interesting questions is, can you figure out who these vendors are in the real world? And of course, the problem in the dark web is the amount of deception. A lot of the vendors are not even real vendors, so there are a lot of scams and so on. So can we build models to sort of distinguish scams from real vendors? Can we link all the information about vendors and try to figure out where they are in the physical world? This one is going to be the subject of our case study. So the penny stock market was the subject of the Leonardo DiCaprio movie. And so there are all these stocks that sell in a market where they are worth pennies, up to or maybe $1. And a lot of scams go on here. So there are a lot of stocks that are being basically falsely promoted to inflate their prices and get people to purchase those stocks. And then the people running the scam just do a sell-off. And the stock plummets, they pocket all the profit and disappear. And these scams actually take over a year to prepare on the internet, and they leave a big footprint there that could be used to detect the scammers and basically disrupt the scams, because even though it is well known that many stocks on the penny stock market are fraudulent, people still buy them. And I suspect that a lot of people lose their retirement on schemes that are too good to be true. So this is also a very interesting domain. And the domain where we have made the biggest impact is the human trafficking domain, where we're basically trying to help law enforcement find traffickers and find victims. And the data that we have is over 100 million online advertisements for escorts gathered over a period of about 3 years. About 50. I forgot 3 zeros on the images. It's 50 million images. And they want to gather evidence. So part of the challenge is that the evidence is very fleeting. Escort ads are often put up only for a few days and then disappear. And law enforcement wants to have a whole trail of information to document the cases against the traffickers. There are many interesting challenges, a very sort of strange Language model, as you can imagine, the language model in escort ads is not the same as Newswire. There are no identifiers. So let me give you a small demo. So can you, I'm gonna ask to turn off the recording because there's a lot of PII for that demo only. So the rest is all okay, yeah. This is a chart from one of the law enforcement agencies that shows some of their human trafficking investigations over several years. And what used to happen is they, they had a lot of domestic violence calls, and over around 2,000. And this little red bar was the number of investigations that they opened based on those domestic violence cases. So people would come in, they would say, my boyfriend beat me up, and then they would not be able to investigate. And around here is when two of these systems were introduced. And so actually the number of cases that they got is much smaller, but the number of cases that they actually investigate is huge compared to what they were doing before. It's over 62% now, where it was less than 1% before. And the difference is that when the case comes in, they can look up in these systems, the information about this person, and they can very quickly ascertain whether there's a chance that the person who beat up this woman is actually a pimp, not her boyfriend. And so in those cases, then they will open an investigation. So this has made an enormous difference. Now, these are some examples of cases that they closed recently. So, man sentenced for 97 years in human trafficking case. This, I think, has been one of the longest sentences that a pimp has received. And again, a lot of the information that was used to support the case was gathered with these systems. This is, accomplices got also arrested. In this case, there were many victims that were, basically identified and tried to, rehabilitate. It's very difficult to get some of these women off the street because of this enormous psychological damage that has happened over these years of victimization. This is another case that's actually very interesting. It's happened in California. So somebody who works for the district attorney actually, does this of human trafficking cases on her spare time, because they have a very small unit. And there was a case of this missing juvenile that was reported in the San Francisco office. And she was able to log in the system, realize that actually this person is being advertised in Georgia. And they managed to rescue her and bring her back. And it just took a few minutes for them to actually figure out that, yes, this person was actually missing and is being advertised online, and it's not in San Francisco anymore, it's in Georgia. So this system, as you will see during the tutorial, is actually quite simple. But the impact is just enormous. And I think in these unusual domains, there is really an enormous opportunity to do what to us, computer scientists, are fairly simple things, just mixed in a new way to actually solve a lot of these problems. So what's different in some usual versus unusual domains? And to me, if you think of a usual domain, you think of news. So people have done extractors and lots of things with news. And there's some good English. Now, the unusual domains, they're going to have a lot of jargon, a lot of ungrammatical text, where your standard Stanford nerd extractor is going to perform miserably bad. The usual domains have mostly correct information. I know there's fake news, but Wikipedia has mostly correct information. Escort ads have mostly deceptive information, except whatever information is needed for the client to reach the escort. Everything else is potentially fake. Age, photos, name, of course. The phone number is not fake, otherwise the client can't get in touch. There's a lot of deception. There's obfuscation, targeted at Google, basically, so that law enforcement cannot look up phone numbers, email addresses, and so on. But a human reading the page can very quickly figure out that what to do. In usual domains, there are often very large reference sets. Wikipedia being one of the most popular ones. And so in unusual domains, there are very few reference sets that are useful. The escorts are not famous people. They don't have Wikipedia pages. In many usual domains, there are very large websites that have a lot of the content that you are interested in. In unusual domains, there is a long tail of many little websites, specialized websites that contain useful information. You would not believe it. There are probably tens of thousands of escort websites that have not one escort, but harder to get. Pages may be ephemeral. They might be in the dark web, and they might actually be in websites with fairly sophisticated anti-crawling measures. I mean, CAPTCHAs being a very simple case of that. So the two guiding questions is, how do we model information in unusual domains differently from how we would just model, knowledge graphs of like DBpedia, like the knowledge graph of Wikipedia? How do we model it? How do we represent it? And then, given the challenges of building the knowledge graph, how do we search it, and what kinds of inference can we do to sort of improve the information and actually derive insight? In the demo that you just saw, a lot of the insight is coming just from analysis of co-occurrence. The system has no model. Law enforcement now suddenly has a tool that is just orders of magnitude better than what they had before, which was Google, for their cases. So let's go a little bit in. So simple definition of knowledge graph is that it's a directed graph where you can have multiple edges between nodes, and the edges are labeled. And they're called facts or assertions, if you don't want to call them facts, because you don't know whether they are true or not. And different communities have different names for this. So there can be a head entity, some kind of relation, and a tail entity, or in the semantic web, it's an SPO triple, subject, predicate, object. So like your person, name, Pedro. And you can have millions and millions of these ones. So here's but this definition is very encompassing, and one could sort of apply it to things that look very, very different. So the idea that you have triples can yield completely different knowledge graphs, and some people in the semantic web would not call this a knowledge graph, even though it fits the definition. So you can make the pages be the subjects, and then you can extract certain terms from them, and they would be the objects, and then you say this page mentions this person. Now, this is a pretty boring knowledge graph because it only has one relation, mentions. But if you think about it, there's a lot of things you can already do with this by just analyzing co-occurrence. You can detect communities. You could do all kinds of interesting things. So I would not dismiss a very simple knowledge graph as a useless knowledge graph. It's actually already very useful. This is also simple and much more useful. In this case, what we've done is labeled the edges with property names. And this is at the core the knowledge graphs that we use in the unusual domains. So we have the subject be the page, and then we have basically properties that we can extract from that page, even though the system doesn't fully understand how they fit together. So the system doesn't understand whether this stock ticker is the stock ticker of this company. This representation only conveys the information that this company and this stock ticker and this promoter appear together in the same page.
I have a question. So I find it unusual that you're labeling the relationship with the properties versus the entities themselves.
Oh, okay.
Is there a reason for that?
Yes. So the question comes up, is this an instance of a stock ticker? Is this an instance of a company? Is this an instance, a promoter could be a company or a person? And so, yes, the reason I'm doing this is that in this so very simple KG, there are no classes. There's only one class, which is page, and there's another class, which is thing. And everything that is not a page is a thing. And so the kind of reasoning that you can do here is more primitive than the kind of reasoning that you can do here. So this is really more the semantic web knowledge graph representation using the language of the semantic web, the resource description framework, or in OWL ontologies. And then you represent things like this, that you say, this Legacy Ventures International is a company, and this other one is also a company, and the promoter of this company is this company, and it has a stock ticker. And as a computer scientist, you look at this and you say, this is much better. I can do all kinds of reasoning with this. This is the way we should do it. And our experience in our projects is, yes, we came from this community. And so we had it ingrained in us that this is the way we had to do it. And it's just not possible. And the reason is that there's no way to build extractors cheaply for so much information that can reliably detect the classes of things and can then create these links. It's much, much easier to do the previous one. And even though we banged our heads against this problem for about a year, we realize that we can actually derive so much insight in the domain with a much simpler representation. It's not necessary to sort of idealize the representation and then say, okay, I'm going to build this representation because I can do all my reasoning that I want there, and then I'm going to just figure out how to put the data in there. Problem is that second part is going to be very difficult. And then, of course, you could even go further and say, well, you know, we actually have a date when this company started being the promoter for this other company. And we have a source of the information where this, you know, this link came from. And so I think this is of the kind of information that you get in Wiki Data, which is this big knowledge graph being crowdsourced. But it's very, very hard to build if you're automating extraction from documents, especially messy documents. So what we do is actually we use something that allows this, except that, as I said before, most of the time this is not going to be a specific class. It's going to be thing or page. But if we can, maybe it'll be a thread or a post, and then there'll be your posts in threads. And so, to the extent that you can structure your information for your domain, you can start to create classes. So that brings me to ontologies. So how about ontologies? So how many people are ontologists? Okay, we have one ontologist in the room. So I will be careful with what I say. Our goal is not to model the domain. Our goal is to help users solve problems. And so the idea is we should model the minimum that we can to help users solve problems. If there's something that doesn't matter to users, even though it seems very important to you as a sort of modeler, don't model it. And so really, I think the idea is let the users create the ontology. They're not ontologists, but they understand the domain. And I'll show you what this actually means. Now, the more deeper the ontology, the harder it's going to be to build extractors for the information and to assemble. So we only need the items that users care about. We can get away with a lot of reasoning that's outside the traditional semantic web. Reasoning about co-occurrence, reasoning about networks, all kinds of things that are coming from machine learning that were not part of the traditional semantic web are actually the reasoners that we use in these unusual domains. Whoops. So the answer is, we build new ones and we keep them shallow. And you will see an ontology that users build for the securities domain in a little bit. So the other question is, how do we store these knowledge graphs? There are many ways. If you come from the semantic web, there's one way. It's a triple store. There are many triple stores, Allegro, Virtuoso, and many others. For people who are not in the semantic web, there's a language called Sparkle that's very similar to SQL, adapted to be able to basically do queries on graph databases. But this is not the only way. There are actually native graph databases, and there are actually a lot of them. And they have languages like GraphQL, Gremlin, Cypher, which are very different from the sort of SQL-like Sparkle languages from the semantic web. And they are popular. Now, the other ones that exist are the NoSQL stores, like key value stores, document stores, and you can have a very simple, say, node-centric model of your data. Basically, every node in your graph is a document, and you store something about its neighborhood, and then you put this in one of these stores. We use Elasticsearch, and many people that work on these unusual domains use Elasticsearch for its ability to do basically fuzzy text search in addition to a fairly sophisticated structured query language that can do filters and aggregations over enormous data sets much, much faster than any triple store can do. And so even though we're stalling knowledge graphs, we're actually putting them in document stores rather than graph databases or triple stores. I think this is a trend that is growing in the community, because when you have 100 million documents which yield about 2 billion triples, it's a lot of data, and Elasticsearch is horizontally scalable, so it runs on a cluster. Yeah, question?
Some graph databases claim that they can manage up to 50 billion nodes and 50 billion relations. Have you tried any of them, like Stardust or the ones that listed here?
No. So we tried Neo4j at the beginning of our projects, and it was just not scalable enough. The reason that we use the NoSQL databases is that they are free. Some of these other specialized databases are not free. Elasticsearch is free, and it runs on commodity hardware, whereas some of the other ones require big, expensive servers.
Do you find that using the document store severely limits the questions you can answer with your data?
It does limit the questions that you can answer, but in one way. So the document store has no joins. So that's something you have to deal with. If you don't have joins, you have two options. You denormalize your data a little bit so that each document contains more information, so you don't need to join to get it. And the other one is you do client-side joins. And so we do client-side joins. So we have a proxy, so we get the documents, and if we need to go one step further, we do that client-side. So we have a sort of Sparkle processor. Mayank will get into that at the end of the tutorial. And the kinds of joins that are useful for our applications are very simple. So we found that in the end, it hasn't actually limited the kinds of information that we allow users to query. So I did some research on the my slides are backwards. Okay. On the popularity of databases, and there's some online site that analyzes basically popularity based on adoption. And so here are basically Oracle, MySQL, and Microsoft SQL Server, popularity over 1,000. Here are things like Postgres and Mongo, more than 100. Redis, Elasticsearch are here at around 100. Elasticsearch has been growing a lot since 2013. It had less than 10, now it has more than 100, so that's a big increase. And here are triple stores, hovering at around 1 or 2 for a very long time. And so it's kind of interesting that basically we have these large data sets that we want to analyze and query. They are getting put in the NoSQL databases, and this one I think remains of a niche market that is not actually growing that much. You can see all these ones are gaining in popularity. And so if you actually look inside, so like which of the graph databases are getting popular, Neo4j is the most popular graph database with the widest adoption. And then the other ones are all mixed up here at around popularity 1. Virtuoso, which was very popular, has been actually becoming less popular. So if you have a lot of data for these unusual domains, our advice is, even though it's a graph data, it's a graph data because it's a knowledge graph, put it in a document store and deal with the joins in a specialized way. And you'll be much happier because your queries will be much, much faster and your hardware costs will be much, much lower. I mean, throughout the tutorial, I'll have very strong opinions about a few things based on experience, and then we also have a lot of things that are based on research published in the community, and I'll try to distinguish that. So, the things I'm saying about how to store your knowledge graphs are based on our group's experience and our experience talking to other people doing similar things, not necessarily based on very careful experimental studies. So, are there knowledge bases that I can reuse? And so, many people may have heard of the Link Open Data Cloud and have seen this diagram that every 2 years gets bigger and bigger and bigger and more connected. And the life sciences are a huge adopter of the Link Open Data Cloud. So if you have an unusual domain that has to do with life sciences, you'll find a lot of interesting reusable data here. Life sciences, because of the amount of funding that they receive, I wouldn't call them an unusual domain, even though they are different from Newswire. Unusual domains are, I think, these domains that receive no funding, but are have a lot of data out there. So the Link Open Data Cloud is a good place to look for reusable sources. Of course, there's DBpedia, the graph database based on Wikipedia, and has 4.5 million things, of which 1.5 million are people, close to 1 million pages, places. creative works, music, paintings, and so on, of close to 500,000, 241,000 organizations. And if you think about it, this is a lot, a lot of organizations. Almost none of the penny stock companies have a Wikipedia page, which means they are not in Wikipedia. So if you want to find out any information about these little companies that are being promoted in the penny stock market, you're not going to find them here. The people who are promoting them, the organizations that promote them, they're not here. So this is great for some things, but in these domains where you have basically non-famous people doing things, you're not going to find them here. Not to say that this is not useful. Yago is also derived from Wikipedia and WordNet and GeoNames, and it has less data than Wikipedia, but it has a very, very nice taxonomy of classes that they derive from the data. So even though you might not find all the data here, whoops. Sorry. The class hierarchy is awesome, and so it's it's very useful to try to put your data into that class hierarchy and then get more data from Yago. Wiki Data is sort of a new, sort of recent effort to try to build a Wikipedia of data. So it's crowdsourced data, and the goal is that if we can build this crowdsourced data, then it can feed all the info boxes in Wikipedia in all languages. Because what happens is, in English Wikipedia, the info boxes are great. Portuguese Wikipedia, much less so. And so the idea is to have all the data that goes into the info boxes actually come from a database. And so there's this effort to build this collaborative, multilingual database, and it's not restricted by the same sort of editorial concerns as Wikipedia, so you can have non-famous things in Wiki Data. And people can contribute it from databases, so it has a lot of things. The penny stock companies are not in Wiki Data either. But it's much bigger, and it's very nice, and it also has a Sparkle endpoint and dumps, and you can use it freely. There's of course things that are not free to use, like the Google Knowledge Graph, which is derived from many sources according to their publication. It was based on Freebase. Nowadays we know less and less about how and what is going on with this big knowledge graphs of these corporations. It powers the knowledge panel, so if I look for the ticker symbol Apple, it'll figure out it's Apple, and it'll show me information about Apple. So Google, all the little panels you get, all the answers are coming from the knowledge graph. And they claim it has around 70 billion facts or assertions. And so there's a lot of interest in the big search engines to build knowledge graphs. And they reuse everything that was in the previous slides, obviously. And then they add whatever they can more. So other knowledge graphs that I find actually very interesting is this one. So you're working on an unusual domain like we were, firearms. We wanted a list of all firearms, which at that time the ATF did not actually have. And we searched and searched, and we found this wiki called the Internet Movie Firearms Database. And it's an awesome wiki. It has every firearm that appeared in a movie. And it has actually the specs of the firearm, photos, and then which movies it appeared on, and which actors used them, it has an enormous, nice taxonomy of all the different firearms, and so it's a resource that for firearms is more complete than anything that you found there. And it's basically, you find all these communities that get into something and build these awesome resources that you can go mine. There's of course Microsoft Satori, which is of Microsoft's knowledge graph. It has actually a very nice streaming API, so you can get streams of all kinds of events that are happening in the world. And so it's worth checking out, because if you're working in unusual domains where bitcoins are useful information, they have all the Bitcoin transactions as a stream that you can tap into. This one, of course, is what you would expect a company like LinkedIn to do, which is basically a knowledge graph of all the companies that they have. And so they have built it. They have, basically 450 million people in their knowledge graph. So it's very likely that everybody that you're looking for in the securities fraud domain is here. Obviously, it's not an open knowledge graph, which is unfortunate. But so this kind of things are happening in the world that I think at a fairly accelerated pace. And I think the companies realize the value of building these knowledge graphs for their own business. So what's the difference between knowledge base and knowledge graph? People use the terms basically interchangeably. Many times the knowledge base is used more broadly. So Wikipedia is a knowledge base, even though we would not call it a knowledge graph. So we tend to use the term knowledge graph to refer to the structured formulation of this knowledge bases that has some way of doing query and analysis using traditional graph algorithms. We don't restrict it to be an OWL RDF data set. So why knowledge graphs? Because they are machine and human readable. So one of the things that we do in our work is once we extract data from a knowledge graph, from a document, we actually keep the document. And we found that the document is often as valuable as the structured data you extract from it, because with Word2Vec and all kinds of text analysis, you can actually derive a lot of insight that would get lost if you threw away the words and just kept this extractions. They are very useful in search and data mining. People have been extending them in all kinds of interesting ways to do all kinds of interesting analytics and work. And it's actually fairly broadly used in many communities. Natural language is building some kind of knowledge graph, data mining, all the network analysis, semantic web. So if you take this encompassing view that anything that has structure and links is a knowledge graph, even if it doesn't have an OWL ontology, then you're in a happier place, I think, doing very exciting work. So how do we do the knowledge graphs in the unusual domains? So there are many challenges. So one is the data skew. There might be a few websites that have a lot of information for you, and then a lot of the useful information is going to be in a long tail. We're not going to have a lot of training data. There's very little labeled data for unusual domains. It's going to be important to do a lot of data exploration, so having a nice way to explore your data is key. It's an also interesting research problem. Have to keep the domain experts in the loop. And ideally, you want to give tools so that they can do things themselves. When you interact with the domain experts, at least when we interact with them, and it's not very as frequent as we wished, you realize that they know a lot that you don't. And you're sort of humbled by sort of the depth of knowledge that they have about how to go about doing things in their domain. And one ought to listen to them. And even though you sort of have ideas about how you want to represent information that would be, from a database point of view, a much more logical way of doing it, we learned that you do it their way, they're going to be much happier. There's basically a multifaceted prediction and inference, and of course, scalability is always a problem. We're dealing with domains where you very quickly get to build things that are much larger than DBpedia. And so, having something that scales is crucial. So, at least, again, this is all my opinionated view. So we want to be able to represent confidence and provenance because users insist on seeing this. If you have a machine that tells an investigator that they should go to an address and camp out their patrol car, they want to know why the system is suggesting that they spend their time that way. And this is true for about everything that comes to an end user that's been distilled to levels of processing. They want to know why the system believes whatever they believe. Otherwise, they don't trust it. So provenance and confidence are very important, and then we represent whatever we can about entities and properties. So we keep it as simple and as shallow as we can. But we record everything about every trip. And I'll show you that later. And then we keep the text as closely to the structured data as we can. So we partition the document into pieces. We extract different extractions from different pieces, and then we keep the piece of text associated with the extractions so that we can use it for relevance ranking in the text search and so on, so that the search works better. Because the basic assumption is that when you extract a knowledge graph from a corpus of documents, it's not a database. It sort of looks like a database if you put it in a triple store, because you can start, you can ask structured queries. But if you think about it with a database, as a database, you ought to sort of make the following, at least I like to make the following analogy. Suppose you took your database and then you took all your tables and randomly erased 30% of the cells. And then, a third of the cells. And then you take the cells that remain and you randomly change the values of the other half to be incorrect or messy. And then you have what you get after you extract it. But then if you did SQL queries, it would not work. Most of them would not return any data. And so when you build a knowledge graph, I try to think about it from that point of view. Yes, it looks like a nice graph of data and so on, but I have to remember how it got there. And that a lot of it is wrong, and a lot of it is missing, but overall it is very useful. So this is sort of the schema that we have, and we fill it in as much as we can. So you just think about this, subject, predicate, object. So one triple. So if I was doing an RDF store, maybe I would just store this and nothing else. And then I would be missing on most of the information that we find useful for the kinds of analysis that we do, like provenance. So we record the provenance, we record the origin, which is the original document, and if we can, we record where in the document this came from. Even if we cannot do it exactly, some extractors are not going to give you the offsets in the HTML page because it can have, but at least I know it came from somewhere in this page, or I think it came from these words in this page. We record the method that was used for extraction, because then we can use machine learning to actually figure out which methods work better in which contexts. If the method gives us an extraction confidence, we record that. Then when we have a triple and it has multiple provenance records, we can do reasoning about the confidences to actually come up with a confidence that the system should believe this triple. Basically, that's an aggregation of the confidences of extraction plus maybe the confidences of the sources. Maybe it's 100% correctly extracted from a source that is known to provide false information or not so, or very biased information. And so we don't have a prescribed schema for how to put the confidences. So these are going to be dictionaries. We can put in there whatever you want. It's a document store. And so the idea is you have a schema that's very flexible. We record provenance, but we don't use prov. We have a very practical JSON representation for this. One thing to remember is if you're recording provenance for essentially close to 1 billion assertions, the provenance is much bigger than the number of assertions. So you have to be very frugal with how you represent it. So it's still useful, but it's not incredibly bulky. So this is what we do, or variants of that in the different projects. Any questions in this part?
Error reduction.
How do we reduce error?
No, what does it mean?
Oh, okay. So I'll give you an example. So if you have very simple extractors, like dictionary extractors or glossary extractors, which are basically based on terms that are popular in the domain. So we use a glossary of cities extracted from geonames, and it has the word Charlotte. Charlotte is a city in the US. Charlotte is also a person name. So we will extract Charlotte as a person name and as a city using a very simple extractor. And if you say, give me all the locations of where this person has been, it will say Charlotte, even though in that context, Charlotte was a name. So we record the provenance, the method, and then we have machine learning techniques that use, say, word embeddings to look at the context of each extraction and try to boost its, it applies a classifier basically and says, okay, in this context, it's more likely that Charlotte is a city rather than a person. And we also look for other confirmation on the page. So did we extract North Carolina from somewhere in the page? And then we can say, okay, Charlotte is probably the city because it's in, it exists in North Carolina. So we have the extractors record what they can, even though some of them are dumb, and then use other techniques to look at all the information collectively to try to reduce the error from the extraction. Does that sort of answer the question? Yeah. And I think there's a lot of research opportunities. There are a lot of research opportunities in doing this kind of work of sort of reasoning collectively about assertions extracted from documents to try to improve their confidence. Google does a lot of that in the creation of their knowledge graph. So how can I build one? And to me, I mean, this is a very simple question. So I have my inputs and I have my outputs. And the question is, how do I go from lots of databases that I may have access to, and the web, which this is 10 to the 13. So I looked up and see, okay, how big is the internet? It says 10 to the 13 pages. Some very, very large number, which for all of us is just way too big. For Google, maybe this is not so big, but for any of us, unless you're from Google, this is way too big. And so, that's part of the problem. So what we're gonna do is we're gonna do some crawling. We're gonna crawl this massive web to maybe download a manageable size that characterizes our domain. Putting here 10 to the 8, up to 100 million pages, is many domains can be this size. Many can be smaller, but it's some tiny number compared to this one. For most of us researchers, it's a big number anyway. And then we're gonna do information extraction. And we're gonna have lots of little knowledge snippets that our extractors can extract. And then we're going to pull them together and put them into a knowledge graph. So this is sort of the typical workflow for building knowledge graphs. And to me, one of the fascinating things is, can we create tools so that experts, domain experts who don't know how to program can do this themselves? Because these unusual domains exist in every organization that, lots of organizations, and they just don't have the money to fund software development for them. And then, but they have people who could do something themselves. And so a very interesting question is, can we create tools so that these users can build useful knowledge graphs where they can do certain kinds of data mining to help them do their job without requiring a natural language understanding person, a data scientist, an information extraction person, a database guru, which is what often requires to build this massive knowledge graphs. So let's go into crawling a little bit. I'm just going to have a couple slides just to give you some context. So the problem is that the web is really very, very big. And I think the web has like 4 parts. So there's whatever Google indexes, which it's a very large index, but apparently can be maybe less than 1% of all the pages that actually exist on the internet, because there's this thing called the deep web, which is basically all the pages that are behind forms, where you have to fill in a form and it gives you a page, and those many times are not indexed. Then there's the dark web. Who knows what the dark web is? Yeah, okay, a few people, so I'll give a few sentences. So the dark web is basically a web that's not connected to our regular IP addresses, and it doesn't have DNS. So it uses a different protocol, the onion size, for example. And you have to have a special browser to be able to reach it, and it guarantees many levels of anonymity, so that I don't know where the web server is, and the web server doesn't know where I am if I'm a client. And so there's all kinds of good things to the dark web, like people in countries where the government is clamping down on information, they can sort of safely provide information to the world in the dark web without the government sort of figuring out who they are. That same level of anonymity has allowed marketplaces to grow for unimaginable things. Everything that you could imagine buying, from drugs, guns, poison, assassinations, child pornography, it can be found in the dark web. And so for many of these domains that we're interested in, even though the dark web is not really drawn to scale, I think if it was drawn to scale, this would be less than a pixel. It's a very rich source of information for some of the organizations. And so the web is very big, and you really want a tiny part. You may want some part that Google indexes. Typically, you may want some parts from the deep web that Google doesn't index. You may want some parts of the dark web. And of course, there might be things in the open web that Google didn't index anyway. So you want to be able to sort of get to all that for your domain. And so the challenges are that you're trying to identify this sort of tiny piece of the web that contains the pages that have the information that you need. And so there are many interesting research challenges here that it's a fascinating topic. How do I find these sites? I'll leave it to that. You start with some seeds, you do Google queries, you try to automatically figure this out, you keep a user in the loop. Once you sort of know how to do this to some extent, maybe you have a few large sites that you want to get data from, you do crawling. And so the challenges here is you need to somehow have machine learning to build a model of what is the relevant part, so that when you send this spider out on the web crawling, it's going to stay focused on the information that is relevant to your problem. Once you've done that, you want to revisit the pages that change dynamically so that your content stays fresh. Downloading dynamic content is a challenge. A lot of the pages are built dynamically on the browser. They are not defined by HTML, they are defined by JavaScript. This has become less of a technical problem because of the headless browsers. So it'll download the page, it'll render the DOM, and then it'll serialize the DOM into an HTML page. It's much, much more expensive computation-wise, but it's okay. There's still challenges like infinite scrolling. Many pages have infinite scrolling, so you keep scrolling, it shows more data. So you need the crawlers to be able to deal with that. Overcoming anti-crawling measures. I'm not advocating people do anything illegal, but many websites have crawler traps. So your crawler will go into some pages, and then the server will keep them going in circles in pages that are actually not ever being shown to users. There can be captchas. There can be OK buttons that people have to click. Are you over 18 years old? So you need a crawler that can actually do these things. Maybe it's human-in-the-loop crawler, where the user solves the CAPTCHA, and then the crawler keeps going. And then exhibiting human-like behavior is something that people work on so that the crawler doesn't get banned or kicked out of forums and so on, where they are monitoring for bots. So in our work, we've always crawled open public information. So there was, if anybody was a user, this is information that they could see. Of course, you always comply with the politeness requests of the website. So how frequently can you download and so on. So it's a big challenge. Gathering the information is a very non-trivial task. A lot of what we'll cover later is under the assumption that you somehow were able to download this big pile of pages. Here are some tools that you may want to look at if you're interested in crawling. So Szekely, I'll fix this URL. Szekely.org doesn't have a /ACHI page. Very generic scraping technology, widely used. Apache Notch, if you're interested in massive crawling, basically you're really gathering hundreds of millions of pages. Notch is a great tool. Deep is an adaptive crawler, which will build a domain, a model of the pages that you are interested in through user interaction, and then launches crawlers that can go both broad, and then they can also hit some websites and go deep inside them. So it'll try to get a broad view of what kinds of sites exist, and the user can say, this particular site I want to download every page from. ACHI is another focused crawler that, similar to this one, it can also do domain discovery and then can go deep in some sites. And Scraping Hub is a service. So if you want pages and you don't want to deal with any of these tools, you can pay them to download pages for you. And the prices are incredibly reasonable. Like for $250, they will crawl like 50,000 pages. So if you need data from some websites and you don't want to, $250 is cheap even compared to what a student costs. And they'll do it for you. And then you can hire them to refresh it, to make it bigger and so on. Worth looking at. So we found that in the last experiments we did, the unusual domains have these long tails. So this is 10 to the 4th. So this is the number of domains or websites in the data that these domain discovery tools crawl. And of course, a few websites account for the biggest number of pages, but there are a lot of websites. So this is Counterfeit electronics, Firearms, securities, narcotics was completely a dark web domain, and USPS, they are interested in identifying fraudulent shipments. So obviously, a lot of crime that ships goods, ships them through the United States Postal Service because it's a package, it just goes by mail, it goes undetected. So information extraction. So we'll start with some generic information about information extraction. So what is it? So you have documents, and you want some form of knowledge snippet. So it's pretty simple. And so traditionally, when information extraction started, it meant I have a piece of text and I want to know what it says. I want a structured representation of what's in the text. Nowadays, when we're on the web, the pages don't look like this. They look like this. And so we're now faced with information extraction from pages that have charts, have tables, have a lot of data. I mean, they will, of course, have snippets of text. You know, that's what appears in blogs and so on. But, I mean, there's a lot more to it than just, extracting from text. So, people have come up with some ways to taxonomize this so that we can make progress. So we can look at the different document features, the scope of the document set, complexity of the patterns, some relevance issues. So in terms of document features, this is of a nice classification. I think it started with Andrew McCallum, and we sort of extended it a bit. So you're gonna find paragraphs of text, and that's fine. You're gonna find, documents where you have grammatical sentences, but now you start to have some formatting information, like bold-facing or a title with it, that you ought to take advantage to actually understand. So what, extract information more effectively. So if you're doing machine learning, this might be features that you want to take into account, basically formatting features. Then you have pages that have a lot of non-grammatical snippets and some rich formatting and links. So one example would be basically a list of tweets. But this happens a lot in any kinds of forums, summaries of information. They are so very cryptic, have a lot of links, and have very dense information. Then of course you have tables. So here's a table of the people associated with this company. And tables are very nice because there's a lot of information in tables. It's a little bit hard, we'll see, because there's a lot of different kinds of tables. And the way people format the tables is very different. But there's a lot of progress being made on that. And of course, there are lots of charts. If you're into scientific literature, there's a lot of information in the charts. So it's possible to extract, people work on extracting data from charts. It's a fascinating world. All the data starts structured, for publication becomes unstructured, and for consumption it needs to come structured again. But the people who have the original structure will never give you access to the original structure. So you have to recover it from the documents. Scope is also a very useful dimension. So we can have a lot of pages from one website. And so they're all going to have a very similar template. But you could have quite a few websites that you're interested in. So you can build a website-specific model to extract information from that website. And if you have a limited number of websites, you can build a limited number of models. Now, you can sort of look at the information a bit more broadly. So I have forums, and all forums look the same. They have threads, and threads have posts, and posts have users, and they have signatures, and so on. So I could try to sort of model the problem as I'm going to extract from any forum. And then, of course, you have the long tail of anything goes. It's the structure is basically unknown to the extractor. And so can we build extractors that can deal with any structure and get useful information regardless of the structure? So, another dimension to look at is the complexity of the pieces of information that we're trying to extract. So we can have a closed set, like the states of the Union of the United States. There's 50 states. it's an easy closed set. There are things like regular sets, like phone numbers in the US. They typically get formatted in very specific language, syntax. And so one can, the number is not infinite, but it's very, very large, so one doesn't have a closed set. But it's a very regular set. Then you can have complex patterns like addresses. The variability in addresses is very, very large. Then you have ambiguous patterns, where you have, like person names in all kinds of different contexts. So you need to understand the context to effectively extract this. And then you have things like obfuscation. So this is an example text that comes from the human trafficking pages, where the phone number is not actually written as a traditional phone number. The reason is, as a user, as a potential client, I know exactly what number to call. As a police investigator, if I put this number in Google, this page is not going to come up. And so, these kinds of obfuscations are very simple. HH 80 roses means $80 for half an hour. So there's a very strong jargon here. And capitalization is random, just for looks. So standard, NER, that's going to look for capitalized proper nouns and so on, gets confused, and it'll extract words like perfect maybe as a name and so on. So this kind of thing confuses your standard tools, we discovered. And so the other thing that happens is that in many of our web pages, in the unusual domains, you're going to have a small amount of relevant content surrounded by tons of irrelevant content that looks similar to the relevant content, but is actually distracting. So this is an escort page. And the relevant content is here, here, and here. All this other stuff is additional advertisements that the website adds here to have me have other things for me to click on. Other ads from the same person, other ads in my geolocated neighborhood, and so on. And so if I'm interested in extracting information about where this person maybe has been and so on, I need to somehow discard all these other locations and phone numbers that I can come from all this other information on the page. And if I'm trying to do this on this wide dimension of any page, then I want to be able to figure out for any page that I have never seen before, where is the main content, where is the distracting content. So I can try to build models of that. So link structure and so on are obviously very good features because the summaries that the websites are presenting to me are always rich in links, because they're trying, if I really want more information, there has to be a place for me to click on. Whereas here is where I already got here, so the information is a little bit different. But so all these very interesting problems. In this tutorial, we're sort of giving you a lot of problems and some solutions, but a lot of just interesting problems. So this is I think what happens in the unusual domains is that we get pages that are anywhere in the sort of dimensions of the kinds of pages that you want, that you have. So we have things with text paragraphs. So in the securities domain, we're going to have a promotional letter for a company that says, this company company does great, they did all these great products and sold this and signed agreements with all these other companies. So this is going to be text. We also, of course, see this, the ungrammatical, you already saw, tables, charts, the scope. We're always going to have a few big sites that we want to extract very precisely. Forums seem to reoccur. And then, of course, we have the long tail. You have all this of different patterns. And you have, so in some sites, active deception, purposeful obfuscation, so doing models to overcome this is very interesting. So it seems like you have to solve too many problems to do useful work in unusual domains. And I think the surprising lesson for us is the opposite. You actually have to solve some of these problems, and then you can make enormous progress. And we'll show you some of that. So of course, currently there's only one universal extractor that can extract from all these pages. That's all us. And machines, not nearly as good. So we have to get practical. We cannot build a sort of thing that reads any page and understands it. What can we do? So first question is, how good does it need to be useful? And this is a good rule of thumb. If you're showing data that you got from pages to end users, you want to make it be of high precision, otherwise users start losing confidence in your system. How high, I cannot tell you, but you want to be in the 80s and 90s so that most of the information that people get is correct, and then there's provenance. They can easily learn that there are things that the system always gets wrong and they ignore them, but precision is important. If the document doesn't come to them, they will never see that it was incorrectly extracted. So recall is, in that sense, less important. But recall is useful for ranking. So if you boost your recall and you use this high recall information for ranking, then you can sort of bubble up relevant documents to the users. And then when you expose the data, that is of higher precision. How long does it take to construct an extractor? And so I'm not joking. So there are extractors that you can define in minutes, or that anybody can define in minutes. And this is great. Some take hours, some take days, and if you're doing this all sophisticated NLP and machine learning, it's a research task, it takes months. And so it depends on what you want to do. We try to stay on this side of things. So what expertise do I need? None. Basically, I need to know my domain, and I have very simple tools. There's one here, patience. Some machine learning methods require a lot of annotation. Simple scripting in Python, regexes, things like that. Machine learning guru. So we focus on tools here. I know many researchers focus on tools here. Once they mature, you can sort of try to figure out how to put them in here. And what tools can I use? And there are many, and we're going to cover a lot of them. So it's unfortunate that the slides are getting cut off a little bit. So here's some practical information extraction technologies that we have used and find useful and can sort of give advice on. So glossaries. So just think of a glossary is just a list of terms. And so this is on your easiest extractor. You just figure out a way to come up with a good list of terms. And then you just run all the text through it. So the effort is assembling a glossary is not necessarily trivial. Some of our users have glossaries. The securities folks have a glossary of all the stock tickers in the OTC market, in the over-the-counter, in the penny stock market. They have a list of all the companies that they track. So, users have glossaries. They assemble these things, and so we can use them for extraction. Expertise is minimal, precision is medium. So it depends on the glossary. If I have a glossary of person names, just first names, it extracts all kinds of city names because there are so many city names that are named after people. The recall, I put it as medium because of formatting. So they, for example, we have a glossary of company names in the penny stock market, or firearm manufacturers, and they say something like blah blah blah, comma, Inc. dot, and corporation, and so on. These names, when they are used colloquially, they don't have the Inc. and corporation and some of the formal names. So you have to somehow have a technique to take your glossary and sort of extend it so that it can have higher recall. And the coverage is wide. You can apply, the nice thing about the glossaries, and we found them very effective, is that you can use them on your long tail, where almost nothing else works. Regexes, they take hours to do. They require a programmer. They can be fairly precise. The recall is typically low for one regex, and then you do more regexes and more regexes, and then you can sort of increase your recall, and the coverage is wide. NLP rules are similar to regexes, and I'll cover this a little bit. There are some very nice tools to actually do this. So it's like doing regexes on tokens rather than characters. The semi-structured extractor is basically going to take advantage of the structure of the page for pages coming from a single website, and I will give a demo of this. Conditional random fields are very often used to extract from sequences of tokens, and you can train your own. They require a lot of annotations. That solves the problem. In the unusual domains, it's often the case that you cannot hire mechanical Turkers to do your annotation because they don't understand what you're asking them to do because of this sort of specialized nature of the domain. You can have a typical name entity recognizer, like the Stanford NER, and there are others. They work great for clean text. The effort is really zero. I mean, you just run it. You can retrain it. Then it requires something like this. It works great when it works great. So for clean text, or if the text matches the text that it was used to train it, it works really great. If your text does not have the same features, then it works badly. And then there are table extractors, and there's been a lot of work on extracting tables. So we're gonna do a sort of extended demo, and I'm gonna show you the system that we gave these users and what they did with it. So I'll let you read this so you understand what they are trying to do. So microcap stock drop. This is the Wikipedia definition. So the users were particularly interested in this, and so the idea is the following. They set up a shell company. So many times these stock takers belong to companies that don't actually exist, in the sense that they don't actually, there isn't an entity that makes what this company is claiming to make. They're completely made up. And there are companies that specialize in setting up these sort of fake companies in a way that if you are if you think you're doing your homework by looking this company up in the internet, you will find it. And you will find it in Yahoo Finance, and you will find it mentioned in blogs, and you will find a history of trading in this company, and this is all completely made up. They're going to hire a group of 30 people who are in the scheme, and they will trade the stocks among each other, and so there are going to be stock trades reported and so on. This company doesn't actually exist. All is completely made up, and so you think you're being thorough by using Google to research this company, and you will find all kinds of documents. The whole process takes about a year and about $1 million to set up. And so you can imagine this is all done very, very well. And then the scheme starts where they start promoting this company, and they will hire promotion firms that specialize in internet promotions. And they will also carefully orchestrate this sort of promotional materials, and then they do more stock trades. And then the price starts to go up, and then people start buying this stock, and the stock price keeps going up. And then they also do a sort of calculated sell-off, so it doesn't sort of plummet immediately. And I don't know the details, but you can think if they invest a year in $1 million, the payoff has to be substantial. And so the idea is, this leaves an enormous trail on the internet. All these documents are there on the internet for us to mine and try to figure out, which of these stocks is undergoing one of these pump and dump schemes. It's a fascinating topic. So these are the websites that they told us were the most relevant websites. As you can see, there's many websites. We're not going to look at them in detail. Now, some of the websites, you look at them and you see the pages, and it's just like, act now. I mean, this is like your midnight commercials on TV, and you see this has to be fake. I mean, it's sort of cheesy, but a lot of people fall for it. So now going back to the ontology, we have 10 minutes, okay. So this is the ontology that they defined. So they sat down at our system and they defined the ontology. And we were not even in the room, so there wasn't an ontologist to say, well, maybe you should do it this way or that way. They just sit down, they discuss, should we have this, should we have that? And this is address, city, compensation amount. So the amount. So you read this and then you realize they really care about these promotions. So they want to know who the promoter is. They want to know how much money the promoter is being paid to promote the stock. And so the industry they're in, the people who are associated with it, and so on. So, when the company was started, and so on. So they define the ontology, and then now they're trying to basically create extractors for this ontology that they define. And notice that, so the guys who did this are users. They don't know anything about, they don't know how to program. They don't know anything. We didn't even call it an ontology. We just told them define the fields that you want. And so they did this. So I'm gonna give you a demo. I think I'm gonna do a small demo before the break, and then we'll continue after the break. So I'll show you how they specify the websites, how they define the ontology, how they define the extractors, how they run the system, and then how to customize the search. Now, these are two guys from the SEC, both investigators who came in the morning. They worked for about 6 hours, and then they left, and that was it. So what I'm going to show you is the system that they built in 6 hours. And from all the extractors that I listed here, I'm going to sort of demo the glossary, the NLP rules, and the semi-structure. So let me do the demo, or at least part of it. Okay, I have to exit PowerPoint. So this is the system that they built. So the ontology shows up here in the query form. Okay, I'm calling it ontology. I know for some people this is like, okay, you can't call that an ontology. But it is the ontology of the system. These are the property names. And you can choose which ones to put in the search form. And so I'm gonna search here, and I'm gonna say act now. So I figured, I've seen this page, like act now, this stock price is not, it's not gonna stay high, for so long, whatever, And so you say act now. And so it gives you an overview of what kinds of pages are in there. So they built. So we give them an extractor for cities. So this comes by default in the tool, but like council, all that, they defined how to extract that. So the stock tickers, so like act now, you can see, I searched as text, so act, there's a stock ticker called act. It showed up there. But here, act now, shareholder, blah, blah, blah. LGYV is about to set the pace. Now is the time to act. Now, I don't know, for many people, this is sort of a dead giveaway that this sounds too good to be true, but this is the kind of information that exists there. And so I actually don't know anything about these companies, but so I opened up this page, the LGYV. I went and looked it up in all the big knowledge graphs, and that company is not there. But it is probably in Yahoo Finance. And you see, it has other stocks that it's associated with, Legacy Ventures International. It's in something in Las Vegas. They got the promoter name. The promoter was paid $23,000 because they have to disclose this to promote this company. And it appeared here, and there's a phone number associated with it. And so, I mean, if you think about it, this is two SEC guys, dealing with all these web pages. They were able to do this. It's kind of pretty exciting. So if you click, you can sort of read the page, the text that our system extracted, but you can also look at the original page. So you see, so basically they were able to make the system pick out these pieces of information from this page. And they did this for 23 different websites in 6 hours. So there's a lot that you can do with very little effort, which to me is very exciting, because once you have data in some form of knowledge graph is when the fun starts for most of the people in the room, which is now I can do all kinds of interesting data mining and get insights and build networks and try to figure out which companies are being promoted and so on based on just extractions that are so cheap to get. So Penny Picks, LGYV offers a unique opportunity to profit from the explosion in demand for packaged water. So they sell packaged water. Sounds like, bottles? I don't know. So, I mean, these are, the information. You can sort of click on the ticker, and then you can get everything that the system was able to extract related to this ticker. So the mentions of places, emails. So Peter at allpennystocks.com and so on are emails associated with this ticker. The cities, organization names. Now, if you're a domain expert, some of these organization names are going to make sense to you as being interesting because they know that there are some organizations that are involved in scams and so on. So, I mean, mind you, this is just, so the way that the system got these organizations is two ways. They gave us a list. They put in a glossary that has all the organizations. And so it just extracted with a glossary. Plus, it also extracts from the semi-structured extraction that I will show you. Paying parties coming from the pages, they were able to do that. Phone numbers, the system extracts automatically. So there's a combination of rich information about these companies that the system is able to pull out. Promoter names, other stocks that get co-mentioned with the pages, and you can see this is probably very noisy because it probably on the right page there are many other stocks that are being advertised on the page, and so indiscriminately pulling them all out. But if you see the trends, maybe this one is actually related to the other one. So I mean, this is the kind of things that you could do some kind of network analysis to do interesting work. And they did this in 6 hours. And so I will show you after the break how they did this, because this is an interesting set of tools that one can use to very rapidly bring up a knowledge graph for a new domain. And, so let's just break for coffee. And we'll start with answering questions and then go